talking about vector fields in 2D and 3D. Let's start 2D. A vector field is technically a function that takes a point as input and gives you a vector as output. Best thought about by example. Let's consider this vector field here. A point is input, xy, with parentheses, and a vector as output, in this case, negative yx, is a vector. Notice the pointy brackets. It is a function. I can evaluate this function at any point I like. For example, at 1, 1, the output is negative 1, 1. At 2, 1, the output is negative 1, 2, etc. I could evaluate this function at infinitely many points. More interesting, though, is to graph it. How? At any point in the plane, like 1, 1, draw a vector starting at that point. So at the point 1, 1, I should put a little half arrows above these F's here, by the way. At the point 1, 1, draw the vector with components negative 1, 1. Draw that arrow right there. At the point 2, 1, draw the vector with these components. Negative 1, 2. Horizontal, negative 1. Vertical, 2. Oh, like that. Now do that for every point in the plane. Yeah, right. Okay. You get a vector field. You get a field of vectors. Technically, infinitely many vectors, though you only draw finitely many of them. They can get very long. For example, f of 10, 10 is going to be negative 10, 10. And the norm of this, the length of this, is square root of 200. 10 times the square root of 2, about 14. Kind of long. Drawing it accurately as an arrow, you get a pretty long arrow. In fact, these vectors would get longer the further away you move from the origin. So when you actually draw these things, yes, you can try to draw them accurately, and certainly you should do so if the instructions say to do that. But with technology, typically what happens is that you scale the vectors down. Now, the most basic command to draw vector fields in Mathematica is vector plot. We can enter a vector field. One way to do it is like this. Using, as standard in Mathematica, curly braces. The curly braces, sometimes they represent points, sometimes they represent arrows. It depends on how they're being used. This is effectively a way to define this vector field and, for example, see that f of 2, 1 is negative 1, 2. Vector plot will plot the vector field. By the way, the extra curly braces inside the input is not technically necessary, but I like to do it with the extra curly braces so that I could allow myself to plug points in if they are truly stored as points in Mathematica in a variable name, for example. If you use vector plot like this, it's going to plot a bunch of vectors in the vector field, except they're not going to have the correct lengths. In fact, Mathematica, most of those vectors are too short. And they definitely, in the vector field, don't all have the same length, but Mathematica is drawing them as if they do. Really, what Mathematica is showing us is something called the direction field. It's got the directions of the vectors correct, but not their lengths. That's okay. it at least gives us a little feel for what you could call the flow of the vector field. Pretending, if you like, that those arrows represent velocity vectors for fluid particles, whether those particles be water molecules or I don't know, what else? Liquid nitrogen, whatever kind of molecules you're talking about, those arrows could be velocity vectors. And again, they're the wrong lengths, so you're not quite getting the speed information. You're losing the speed information, but you are seeing a circulation going on, if this was accurately modeling some fluid flow. So the first conceptual point here is to understand the idea of a vector field, plugging points in to get vectors out and then graphing them, though again, vector plot is not really, it's showing us the right directions, but not the right lengths. By the way, at the origin, the output is the zero vector. That's not literally graphed in this picture. You could graph it by plotting a single dot at the origin. And it often is a good idea to do so. In fact, I'll do that. One way to do that is with list plot and plot individual points like 0, 0. Make it a big dot in the middle. To emphasize the vector field is the zero vector there. That's actually pretty important. Some of you have had diffie-q with linear. You know, we did a lot of this in diffie-q with linear. Some of you have not. You have that to look forward to in the fall. Vector fields are done a lot in diffie-q with linear. But the emphasis is different. In diffie-q with linear, differential equations with linear algebra, the emphasis is under understanding the flow of the vector field in terms of what are the solution curves, so to speak, what paths do the molecules trace if this were a fluid flow. By the way, if this were a fluid flow, it'd have to be a thin sheet of fluid, effectively two-dimensional, which I suppose you could create by putting water between two plates that are really close together. So it'd be a two-dimensional fluid flow. So we're interested in the paths of the water molecules in differential equations with linear algebra. Here, yeah, we are still interested in the paths, but we're also more interested in integrating this vector field effectively over various paths. And what's going to be the main application ultimately, though we won't talk about it a ton, is, for example, if this were a force field or some gravitational force or some electromagnetic force, I'm not saying it's accurate. If it were a force field, the integral would give us the work done by the force over the path. It's kind of a big application of integration of vector fields. Not saying that's an accurate force field for any gravitational or electric magnetic force. I'm just saying we could think of it that way. For today, though, our objective is simpler. We do want to think of it in terms of fluid flow. And we effectively want to differentiate this vector field today. Starting Friday, we'll integrate it. But today we want to differentiate it. What? Differentiate a vector field? And there's two kinds of derivatives of vector fields. They're called divergence and curl. Heard those names before? Divergence and curl. Divergence is a kind of derivative of a vector field that's going to give you a scalar quantity. Gives a scalar quantity. And it's got a certain kind of funny notation. We use the gradient operator, del or nabla or d, if you want to call it d, and dot it with the vector field. This kind of derivative of a vector field is thought of as a dot product, where the del is a vector of operators, and the F is your vector field. And the standard notation, it's a little weird, but the standard notation for this is to call the first component M and the second component N. M and N are functions. So is F. These things are functions of X and Y. M and N being scalar valued, the kinds of functions we've been talking about recently with partial derivatives and directional derivatives and optimization and gradients and integration, double and triple integrals, have all been scalar valued functions. When you put them together in a vector, you get a vector field, a vector valued function. How can I put ddx and ddy in a vector? Those are not numbers. They're operators. Do the dot product here as if it were a multiplication. Let me initially write it like this. ddxm plus ddxy. As if it were a multiplication. But it's not really a multiplication of the operators with these functions m and n. These are operators. It means take the derivative to get this. It's just a convention, a convenient convention for representing an operation, a differentiation operation. These are not literally numbers, and these are not literally multiplications. You kind of pretend they're multiplications for the purpose of getting to the formula. Operators are actually functions that map ordinary functions to other ordinary functions. In this case, we're mapping a function m to its derivative dm dx and a function n to its derivative dn dy. And the divergence operator adds those two derivatives. I could say this is what the divergence is without writing that. But it's kind of nice to write this in some context. This does have another symbol. It's called div-f, is another symbol for it. So we might wonder, for example, what's the divergence of this example? Back up here, this is the m, and this is the n. So if the function is negative yx, and notice, by the way, I'm continuing to suppress now the of xy. That is traditional to suppress it because it's just a time saver. But you always want to remember conceptually in your mind that these things are functions of x and y. And here are the formulas for m and n. The divergence of this, written in two ways, is the derivative with respect to x of negative y plus the derivative with respect to y of x. 0 plus 0 is 0. This has got zero divergence. Talk about what that means in a bit here. The other kind of differentiation operator, at least with three-dimensional vector fields, which I will talk about in a few minutes, gives you another vector field. But with a two-dimensional vector field, gives you a scalar. It's called the curl. Gives a scalar for a 2D vector field and a 3D vector for a 3D vector field. Actually, in the 2D case, you also could think of it as a 3D vector, though the first two components of that vector are trivial. They're both 0. Curl F is written again with the del or nabla operator, but with a cross product instead of a dot product. And for a 2D vector field, we think of it as a scalar quantity, and it ends up being the partial derivative of n with respect to x minus the partial derivative of m with respect to y, where m is the first component and n is the second component. So f has components m comma n. So for our example, if f is negative yx, that means the curl of this, using either notation, derivative with respect to x of x minus the derivative with respect to y of negative y gives 1 minus negative 1, 2. Something non-zero, but constant. Doesn't depend on x and y in the end. In general, it could depend on x and y. These things do take on more meaning, more significance maybe, though they're harder to understand in 3D. In 3D, in the general setting, we write f as a function, a vector valued function, a vector field that has 3 component functions, m and n, or should I call it O? Well, that's confusing because O is often the origin and it often looks like a 0. So let's use P instead. The divergence of f, del dot f, now these are 3-dimensional vectors, a 3-dimensional derivative operator vector dotted with the vector MNP. That's just convenient notation. That means differentiate the first component with respect to the first variable, add the derivative of the second component with respect to the second variable, add the derivative of the third component with respect to the third variable. And the curl of f, curl f, shorthand written del cross f, is literally the cross product of these things, of these 2 3-dimensional vectors, although this first vector is not a numerical vector, it's a vector of operators. Symbols for derivatives, not numbers. And well, remember we did cross products way back when? And we made those matrices and we added columns and did arrows. I always forget how that goes. I remember how the cross product goes thinking about a determinant where I hat, j hat, and k hat are the top row. These derivative operators are the second row. And the scalar vector, the vector field components are the third row. I am sort of old school here and remember formulas for determinants of 3x3 matrices, procedures for those determinants better than I remember the procedure for doing all those arrows everywhere. I mean, you added those first 2 columns, I think, and you went zoom, 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 and zoom, zoom, zoom. But I'm afraid I'm going to get it wrong if I do it that way. I expand what's called a cofactor expansion across the first row. So I take I hat times the determinant of the matrix obtained by deleting the first row in the first column. By the way, the absolute value signs is just shorthand for determinant. Doesn't mean I'm getting a positive quantity. Then I subtract j hat times the determinant that I get by crossing off the first row and first column. First row and second column, excuse me. And it's a minus sign there. And then plus k hat times the determinant of the matrix I get when I cross off the first row and third column. I did talk about this. Your memory may be quite fuzzy. In the end, if I write the final answer without I hat, j hat, and k hat, but instead use components with pointy brackets and commas, I'm also going to use subscripts for derivatives to keep it more manageable. The first component is going to be the derivative of this thing, or the determinant of that. It'll be derivative of p with respect to y minus the derivative of n with respect to z. Second component is going to be the opposite of the determinant of this matrix. I could emphasize that by putting a negative sign in here like this. Or I could distribute the minus sign through and write this as negative mz minus p, or let's see, no, mz minus px. Again, the subscripts just mean derivatives. And the third component would be nx minus my. Now you can compute the curl without doing all this stuff. But I wanted to redo it to show you can. It does match the formula in the book without doing all that stuff. Yep, I'm looking right here. Py minus nz, mz minus px, nx minus my. That is what I have here after simplifying that one. That's a z, by the way, where I'm pointing there. Most of your problems for Friday are just computing these things. Divergence and curl. Getting in general functions of x, y, and z for three-dimensional vector fields, or functions of x and y for two-dimensional vector fields. You're not really asked to interpret them, though the author does write about how to interpret them. And in the 4 minutes we have remaining, let me give you a little hint about how to interpret them. This is not the end-all be-all of explanations. Okay? You need time for this stuff to sink in. Effectively, divergence measures divergence. It measures net flow out of small regions. Measures net flow out of small regions. Pretending, and this is really important for fluid mechanics, if you got to take fluid mechanics, pretending the vector field is a velocity vector field for a fluid, a steady state fluid, because it's not changing its behavior over time. For differential equations people, it's an autonomous system. If you evaluate the value of the divergence, which is a scalar quantity, whether the vector field's two-dimensional or three-dimensional, you're going to get a number. Could be positive, could be negative, could be zero. If it's positive, then there's a net flow out of a small region. Take a small region like a circle in 2 dimensions or a sphere in 3 dimensions, and think about the vectors in the vector field near that small region. Some of them might be pointing into the small region, some of them might be pointing out of it. If somehow this is reflecting more fluid flowing out than flowing in, then the divergence will be positive. If there's more fluid flowing in than out, then the divergence is negative. If the amount of fluid flowing in and out is the same, then the divergence is zero. Now you might think for ordinary fluids, real life fluids, that the divergence would have to be zero. That the same amount of stuff in any small region, same number of molecules, has to be going in per unit time as going out for it to be a realistic fluid flow. And I think that's true. Those are called incompressible fluids, at least. Maybe there's compressible fluids that don't behave that way. But you would think for most fluids that should happen. The divergence should be zero in most realistic fluid flows. For our example, the divergence was zero for our curling example. So maybe that's a realistic model. I mean, we're not taking into account things like the speed of light. Like in that model, if you go out from the origin far enough, the molecules are moving faster than the speed of light. can't happen. But as far as the fluid laws go, it could. And the curl measures, you might say, tendency to rotate, tendency for small corks to rotate when the curl is not zero. For a scalar curl, for a two-dimensional vector field, if it's positive, there'll be a tendency for a curl, a small cork in the fluid to rotate counterclockwise being the positive rotation. If it's negative, it'll be a tendency to rotate counterclockwise. If it's zero, then it won't rotate. For a three-dimensional vector field in fluid flow, the cork has sort of like an axis of rotation. It tends to rotate about an axis of rotation, and the curl has a length telling you how fast it tends to rotate, and a direction telling you what direction, determined by the right-hand rule. If your thumb points in the direction of the curl vector, your fingers are going to point in the direction of rotation of the small cork. How realistic this is as a model is beyond the scope of this course. That's for fluid mechanics. We don't have to worry about how realistic these things are, okay? We can pretend they're realistic.